All right, so first of all, this week is the third lab exam, the last lab exam. And it's going to ask questions related to all the lab activities we've done. If you can't make it to your lab, but you can make it to the other one, feel free to switch. And so this is going to cover all lab topics. Anybody have any questions about that? Okay. So, and what we're going to do is, so the test itself will be pretty short. You'll take the test, and then you'll give that to me, and I'll give you the post-test of that bubble sheet test that's like half an hour long. You'll be out of it between an hour and a half total. It won't take very long. Some people, I'm sure, will get done faster than that even. Okay. Anybody have any homework questions you'd like me to go over? Okay. Well, we're getting into the last topic. We have 2 days to do the last topic. This is rotational kinetics. Or sometimes you'll also see it called rigid body kinetics. And the big change here is, remember, up until this point, we've been dealing with nothing but particles. And particles, so up until now, it's just been particles. And particles have no length dimensions. And you can't say anything about the orientation of particles. You can't say the head is facing this way and now the tail's facing this way and stuff like that, because it's all just at a single location. With rigid bodies now, we're going to include both of these. So objects are not going to exist at a single point. They're going to have lengths. And we will be able to talk about, okay, now this part of the body is facing this way. Now later, the same part of the body is facing that way. Okay, that's going to be new. And the first thing I have to talk about is angular velocity and angular acceleration. So angular velocity. Angular velocity is a directional quantity, so it does give you directional information. That tells you how quickly and in what direction an object's orientation is changing. All directional quantities have directional information and magnitude information. So I'm going to think of this the same way, even though this isn't really a vector. Well, it turns out it is a vector, but in this class, we're not going to think about it that way. So the magnitude of the angular velocity is the angular speed and RPM is an example of an angular speed. Okay, so if you have a motor that's going at 2,000 RPM, that's 2,000 rotations every minute. Okay, so that tells you that you're going through 360 degrees of rotation 2,000 times over the span of a minute. That tells you how fast it's rotating. Okay. And then the direction of the angular velocity so that tells you, is it spinning clockwise or counterclockwise? Okay, if you had to choose which one of those you'd call positive and which one you'd call negative, you definitely pick clockwise positive. And so physicists are like, nope, we'll make counterclockwise positive. Screw you. So that's how it is. So we don't get to choose. So a positive angular velocity means that it's rotating counterclockwise. And negative means clockwise. The units that we're going to use for angular velocity, for angles, we've been using degrees this whole semester, and anything where we're going to end up using cosine and sine, we're still going to be using degrees. But the units that we're going to use for angles with angular velocity and angular acceleration is radians per unit of time. So in general, the units are these. And that means that the SI units for angular velocity are radians per second. Okay, so let's think of some kind of RPM thing, and we'll put that into SI units and express it as an angular velocity. So let's say a top is spinning clockwise on a surface at an angular speed of 10 rotations per second. What's the angular velocity? We are always going to denote angular velocity with the Greek letter omega. It looks sort of like a scripty round W. So this is the angular velocity. And it's always equal to plus or minus, and then the angular speed, which is, in this case, 10 rotations per second. This is clockwise, so is this going to be a positive or a negative 10 rotations per second?
Negative.
Yeah, we have the negative. And now we're going to convert this into radians per second. We have it in rotations per second. So now we're going to go negative 10 rotations over seconds. And one rotation is how many radians? 2 pi. So 2 pi radians is one rotation, and I'm doing this just like any other unit conversion. So the rotations cancel, and you end up with negative 20 times pi radians per second. Okay? We could put that in decimals as 62.83 negative. We are only going to be using angular quantities with rigid bodies where there's some point on the body that's fixed to the ground. That means like with a hinge or a pin or something, and the thing just rotates around this point, okay? So our rotations will always be around a fixed point. And you can think of that as like a hinge or a pin or something like that. During the rotation, every point on a rigid body has a different velocity vector. Okay, so every point on the rigid body has a different velocity vector. But the whole body has the same angular velocity. So the entire body has a single angular velocity. The relationship between the angular velocity and the speed v of a point on the body is the speed is equal to the absolute value of omega. I'm just going to put that as like a capital Omega times r. So this is the absolute value. Just drop the negative if there's a negative of the angular velocity. And r is the distance from the fixed point to the desired point. And what you need to remember in order to figure out the direction of the velocity vector is notice every point on a rigid body is in circular motion around the fixed point. Okay. So let's do an example. Let's say we have this L-shaped thing. And let's say this length is 1 meter. And this length is 1.5 meters. And let's say the fixed point is right here. Okay. It's called a fixed point because the velocity of that point is 0. Okay. That's like, okay, if this thing's rotating, if my finger is the fixed point, that point isn't moving at all. Every other point is moving in a circle around that fixed point. Okay. And so let's figure out two things. Let's figure out the velocity vector of this point A, and let's figure out the velocity vector of this point B. So if the angular velocity of this body is positive 5 radians per second, what are the velocity vectors of points A and B? Well, first I'll do A. So let's visualize the circle that A is moving in, okay? It's something like this, right? The angular velocity is positive, so which way is this point moving around that circle, clockwise or counterclockwise? Counterclockwise, and so from that you know that the velocity of A is in this direction. Is everyone with me on that? Okay, well, the magnitude, the speed, is equal to 5 times the distance from the fixed point to A. What's that distance? 1 meter. And so you get a speed of 5 meters per second. And now we can put that into the vector, the velocity vector of the point A. That's in the positive x direction. So this is just 0 meters per second. Okay? And now what about the point B? Well, B is moving around a circle like this. It's still moving counterclockwise, so the velocity of that point B is this. So it's in the positive y direction. The speed of the point B is 5 times 1.5, so 7.5 meters per second. And now that we've already figured out it's in the positive y direction, the velocity vector of that point B is 0, 7.5. Anybody have any questions about that? And you can see, we have this fixed point here. The closer the point is to the fixed point, the slower it's going to be moving. You know that from like playing on carousels and stuff. If you can get into the middle of a carousel, you don't really feel any acceleration. All you feel is your body just turning around with the carousel. But if you're out on the outside, you're feeling a lot of acceleration and you're in danger of flying off. It's because you're moving so much faster when you're out at the end. Okay? The next thing we need to talk about is angular acceleration. This is going to use the Greek letter alpha. Looks like a goldfish. I guess let's put that up here too, that angular velocity uses the Greek letter omega always. Okay, the angular acceleration, well, acceleration always tells you how quickly a velocity is changing of some kind. And so angular acceleration tells you how quickly the angular velocity is changing. So this measures how quickly omega is changing. If, let's see, if omega and alpha have the same sign, do you think the rotations are speeding up or slowing down? Speeding up, that's right. It works just like velocities and accelerations. And if they have opposite signs, then the rotations are slowing down. Just like with angular velocity, so like with angular velocity, every point on a body has a different tangential acceleration. But a single body only has one single value of angular acceleration, okay? So the whole body has a single angular acceleration. Yes?
So you mentioned tangential acceleration for individual points.
Yeah.
How exactly does that work?
Yeah, well, with both velocity and acceleration, it basically works like every single point is moving in a circle around the fixed point, you know? And so the tangential acceleration just has to do with what individual circle and what point on that circle the body is on. Okay. And that's exactly what we did here. You know, we figured out the circles that those points are moving on, and then we used what we knew about circular motion to figure out the directions.
Okay. So centripetal acceleration wouldn't really factor
in. It just doesn't factor in, that's right. It's every point has a different centripetal acceleration too, but I'm just not going there right now.
Okay.
Okay, so now there's a relationship between the angular acceleration and the tangential acceleration of a point. And that is the absolute value, the magnitude of the tangential acceleration is equal to the absolute value of alpha. I'm going to just write it as this Greek letter alpha times r. So this is the absolute value of alpha. And this r means the same thing that it did in angular velocity. This is the distance from the fixed point to the desired point. Okay, let's do another example. So let's say you have this body and the fixed point is right in the middle. And let's say this body has an angular velocity of negative 12 radians per second. And an angular acceleration of negative 40 radians per second squared. What are the velocity vector, the tangential acceleration vector, the centripetal acceleration vector, and the total acceleration of the point A. Okay, so let's make the point A over here. And we'll say that the distance between those is 0.5 meters. Okay, well, this really is just a circular motion problem. We're just using some of these new variables that we've defined. So let's think about the circular path that this is on. It's going to be following a circle, something like that. Okay. The angular velocity is, it's negative, so that's a clockwise rotation. Okay. And so the velocity of this point A is in a direction like this. The angular acceleration is also in the same direction. It's speeding up, that means. And so the tangential acceleration has to be in the same direction as the velocity, so it's this way. What direction is the centripetal acceleration at that point? Toward the center, yep. And so now we can just start filling this stuff out. Just little by little, we're just working through what we know. Okay, so the velocity vector. Well, we know the speed is the absolute value of the angular velocity, so that's 12, times r, 0.5. And no dimensions matter for this shape except just the distance from the center to A, the fixed point A, okay? And so this is 6 meters per second. We already figured out that the velocity is in the direction of positive y. So the velocity vector of that point A is 0, 6. Okay, now let's start doing the acceleration stuff. We have the directions. Let's first do the centripetal because that's what I usually did when I did examples for circular motion. We know that the magnitude of the centripetal acceleration is v squared over r. And so that is 6 squared divided by 0.5. And so that's 72 meters per second squared. We figured out from thinking about the circular motion that that's in the positive x direction. So the centripetal acceleration vector is 72, 0. And now we can think about the tangential acceleration. The magnitude of the tangential acceleration is the absolute value of the angular acceleration, which was, so that's 40. Times r, 0.5. And so we get a tangential acceleration magnitude of 20 meters per second squared. From the picture, we figured out that's in the positive y direction. So the tangential acceleration vector is 0, 20. And that means that the total acceleration is just the sum of these two parts. And so it's 72 in the x direction, 20 in the y direction. Anybody have any questions about that? Okay, I'm going to do another similar example and just give you time to try to think through it. So let's say we have a circular object. And this is the fixed point at the center. And let's say that the point we care about is here. And we'll say that the angular velocity of this body is 15 radians per second. The angular acceleration of this body is negative 30 radians per second squared. The radius of this circle, I guess I don't want to draw it there. Okay, so the radius of this circle is 2 meters. So calculate the velocity vector of that point A and the acceleration, the total acceleration vector of that point A. And to calculate that total acceleration, remember you're going to do that in two pieces. You're going to do the tangential and the centripetal and then add them together. So take a few minutes and see if you can think through this, and then I'll go. So first let's draw the pictures. The angular velocity is positive, so is it moving clockwise or counterclockwise? Counterclockwise, so the velocity is this. The angular acceleration is negative, so is it accelerating clockwise or counterclockwise? Clockwise, and so the tangential acceleration is like this. The centripetal acceleration is toward the center. And now all we need to do is put these pieces together and figure out the magnitudes of those vectors. So for the velocity, we know that the speed is equal to 15 times 2, so 30 meters per second. It's in the negative x direction, and so the velocity of A is negative 30, 0. For the acceleration, the centripetal acceleration magnitude is v squared over r, so that's 30 squared over 2. This is a huge acceleration of 450 meters per second squared. Okay. That is in the negative y direction, so the centripetal acceleration vector is 0, negative 450. Okay. Then the tangential acceleration, the magnitude is 30. This is the 30 from up here, not the 30 that happened to come from the speed. Times r, so that's 60 meters per second squared. We figured out that that's in the positive x direction. So this is 60, 0. And now put those together, and the total acceleration is the sum of those two. So 60, negative 450. Anybody have any questions about that? Okay. Now, the main reason that I introduced angular velocity and angular acceleration is the next thing that we're going to talk about. And this is, I'm going to call this rotational Newton's second law, or the rotational version of Newton's second law. Remember, Newton's second law says add up all the forces on a body, and that's equal to the mass times the acceleration of the body's center of mass. Okay, you've been seeing that all semester. The rotational version of this, rotational Newton's second law, that's how I'm going to abbreviate that one, says take all of the moments produced about some location A. That's equal to the moment of inertia around that point A times the angular acceleration. And the reason I brought up Newton's second law before I brought this up is I want you to notice how similar these are in form. You know, we have to define two of these things still, but this moment is the rotational version of a force. Okay? It's not really a force, it's something a little bit different, but it acts the way a force does in producing rotations. And this I is the rotational version of mass. And obviously that angular acceleration is the rotational version of acceleration. And so if you can remember Newton's second law, you can remember this, okay? You should store it in the exact same part of your brain. You know, they're the same thing. One is just all the rotational stuff. One is all the linear translational stuff. And so before we start using this, I have to define what these things are, okay? So first, we have to define MA and IA. Okay, so the first thing I'm going to define is the moment of inertia. That's the IA. Okay. And so we're going to calculate the moment of inertia about a fixed point. Does anyone remember way back when I first introduced mass, what I gave you as the definition of mass? I said I defined it as a resistance to an acceleration. Do you remember that? And I talked about how, like, in space and on the space station and stuff to measure mass, they actually apply known forces to people to see how they accelerate, and then from that they figure out the mass, because you can't use scales if there's no gravity. Well, this is the same thing, but for rotations. So you can think of the moment of inertia as a body's resistance to rotation, okay? So a body's resistance to being rotated around the fixed point A. Okay? So something that's very hard to rotate, something that's really big and has a lot of mass, that's going to have a high moment of inertia. Something that's really small, not very far spread out, has a small mass, that's going to have a small moment of inertia. Intuitively, what it takes to have, a high moment of inertia is to have mass spread far out away from the fixed point. Or mass is distributed far from the fixed point. And a low value of the mass moment of inertia is when the mass is distributed close to the fixed point. Okay, so let's think about some examples from sports, like Olympic sports. Let's think about diving or gymnastics where people are doing flips and stuff. If somebody's doing like a double flip, say, there are different ways they can position their body, and the body position determines how many points you get for the difficulty of that move, okay? So one way you can do a double flip is like this. Where you pull your body in as tightly as possible. You're flipping this way. Okay. And another way you can do it is kind of the other extreme is with your body stretched out like this. Okay. This can be the same person. Maybe they're doing with their body stretched out like this at the start of their routine when they're still fresh. And then this is at the end. You get a lot more points for doing a double flip with your body in this laid out position like this than you do for this. And the reason is, notice that this is almost as far as you can get your mass spread out from, well, in this case, what we're thinking of as the fixed point is the center of mass of the person. So you can think of that point there as the fixed point. In the laid out position, all the mass is spread out as far apart as they can get it. In the tuck position, everything is as tight to that point as they can get it. So this is a high mass moment of inertia. And this is a low moment of inertia. Okay? And the reason you get more points for the one with a high moment of inertia is because it's a lot harder to get your body rotating in that position. So you're never going to be spinning as fast, which means if you're just on like floor in gymnastics and you're going to do a double flip in the laid out position, you have to get really, really high in the air, and not very many people can generate enough power to complete two flips like this. This one, that's still hard, but compared for those guys, it's relatively, much easier because you have the low moment of inertia. So really quickly, you can go from not rotating at all to spinning really fast. And so you can be pretty low and still finish 2 flips like that. Okay, so that's the idea of moment of inertia. The units are kilogram meters squared. Well, hold on. I should say the general units are mass times length squared. And that means that the SI units are kilogram meters squared. This can never be negative. So notice, this works the same way that mass does. So just like mass, moment of inertia is always just a positive number. Okay? The only things that we're going to need a moment of inertia for in this class are rectangles with the fixed points at different locations. So this is just a diagram of the moments of inertia of rectangles with various fixed points. Okay, so here's the rectangle. We'll say this is the length L. And this we'll call the width W. And here are the different fixed points that we're going to be dealing with in problems. So one, we'll call that A, is right at the middle. Then there are 2 that are equivalent here and here. Then there are another 2 that are equivalent here and here. And then there are 4 equivalent ones at the 4 corners. And the formulas are like this. If the fixed point is at the center, the formula is 1/12 times the mass of the body times the quantity length squared plus width squared. If the fixed point is at either one of those 2 B's, then the formula is 1/3 times m times L squared plus 1/12 times m times the width squared. If it's at either of those points C, the moment of inertia is, you just flip the order of these, so it's 1/12 times the mass times length squared plus 1/3 times the mass times the width squared. And the last one, if it's at any of the 4 corners, it's equal to 1/3 times the mass times the quantity, length squared plus width squared. Okay? So now the last thing I have to define before we can use that rotational version of Newton's second law is the moment of a force about a fixed point. And the way it works is if you have a body, this is just supposed to be some random object. And if that is the fixed point, so I'll call that A. And then let's say that a force is applied at some other point. Okay, so this point P is where the force is applied. Okay, now notice if I draw a line from between A and P, okay, then the force that we apply at P, it could be perpendicular to this line. Most likely it won't be, but it could be, right? So, but for now, let's say that that force is perpendicular to that line. Okay, so we're going to apply a force F like this. And notice that these two are perpendicular, okay? So if the force F is perpendicular to the line from A to P, then the moment about A is plus or minus the force times the distance d, where this is d. Okay, so this d is the distance from A to P. Okay, and then what about the plus or minus? The plus or minus is going to be positive if that force would cause a counterclockwise rotation. And it's negative if that force would cause a clockwise rotation. So you always have to think about the direction of the rotation that that force would cause. So let's think about this example here. So get oriented on this picture. You know that A in red, that's the point that's fixed. That's like the hinge. So if the thing is free to rotate around that point A, would that force F make it rotate clockwise or counterclockwise around A? Clockwise, yeah. I mean, you could use a sheet of paper always and sort of figure it out, you know. So this would be A. That force is acting this way, up, you know. And so you can see that makes it rotate clockwise around that point. Okay? this sort of goes along with your understanding of a lot of things. I mean, you're used to how this works. Intuitively, think of a wrench. So think you're trying to turn this stuck bolt. With a wrench. And say you know that you can apply 300 newtons of force, okay? And think about where you would want to apply it. Would you want to apply your 300 newtons here? Or here? Or straight down here? In order to turn this? Well, you know from experience that if you apply the same force at all of these, the biggest chance of getting this thing loose would be applying the force over here, okay? And it has to do with that moment. The distance from, so this is our A, the fixed point. This is our P. And so this is the distance that's perpendicular to the force. And so we have a much bigger moment that we're producing, a much bigger, you can think of it as like a rotational version of a force. If we apply that force way out here, if we apply it here, you get half as much, rotational generation for the same amount of force. If you apply it here, this could be 50 billion newtons, and it would never turn this thing at all, because that distance is 0. Okay? Before, eventually you'd apply such a big force that this bolt would just rip right off the wall, but it would never turn for an instant, So this would be like a lot of rotation. This would be no rotation. Okay? Let me do one example problem and then we'll get out of here. So let's say that we have a board and the fixed point is over here. And let's say the thickness of the board is 10 centimeters, so 0.1 meters. And the length of the board is 1 meter. What's the angular velocity of this board if gravity is acting down, so this direction is down. Oh, and I didn't give a mass yet, but let's say that the mass is 3 kilograms. Okay, so what's the angular acceleration? Well, let's just do that. That's good enough. Okay, well, the first thing we're going to do is draw a free body diagram. Always at the fixed point, you're going to have an unknown force, so an unknown x and y component, and you can just call that a force vector r or something. You give it any name you want. That's not going to come into the rotational calculation. Besides that force that's applied to the board by the fixed point, what other forces are acting? There's only one more. Gravity, yep. And that always acts at the center of the body. Okay, So be sure you always put the weight force at the body's center. And in this case, that's a force of 29.43 newtons. Okay, and now we just have to calculate the moment of inertia and the moment produced by those forces. And we can calculate the angular acceleration. The moment, so I'll call that point A. The moment about that fixed point A is 1/12 times the mass times 1 squared plus 0.1 squared so that is 0.25 times, so I think it's basically just 0.25 if you round it. No, it's not. Sorry. I got to move this over a little. So this point, fixed point here, is like one of these at B. Do you see that? And so I have to use that formula. So this will be IA is equal to 1/3 times 3 times 1 squared plus 1/12 times 3 times 0.1 squared. And so that is that just comes out to be 1.00. Okay? And now we have to think about the moments produced by each one of these forces. Okay? What about the force R? Well, we don't know what the magnitude is, but it doesn't matter because the distance from R to the fixed point is 0. Okay? So this is some force R times 0, and it's just equal to 0. And now let's do it for the weight force. So this is the moment produced by mg. This is plus or minus a force of 29.43. What's the distance from the about point to where the force is applied? 0.5, yep, it's half of the length of the board. And would that force make it rotate clockwise or counterclockwise around A? Counterclockwise, so it's positive. And so this is positive 14.715. And now we'll put all this stuff together in the moment equation, the rotational Newton's second law equation. We have 0 plus 14.715 is equal to 1 times alpha. And so alpha is equal to positive 14.715 radians per second squared. Anybody have any questions about that? Okay, that's all.